All right, Chapter 8, The Basics of Chemical Bonding. So in this chapter, we're going to take a look at the necessary conditions for bond formation. And a lot of this is going to seem like stuff you kind of already know, and we're just going to expand on it. We're going to examine the factors involved in ionic bonding. We'll write electron configurations for ions. Some of you might already be able to do that. We'll draw Lewis symbols for atoms and ions. We'll look at dot structures. Describe covalent bonds, the octet rule, and multiple bonds. And again, if you had 110, you'll probably be able to do a lot of that already. We're just going to expand on it. Understand the energetics of bond formation. Now that's probably where the rubber is going to meet the road. That'll be some of the new concepts we just saw in our heat chapter combined with bonding, which you probably didn't see in 110. All right, we're going to look at trends in electronegativity. Again, that's old hat stuff. Examine how electronegativity affects bond polarity. That you may or may not have seen. And again, we'll draw Lewis structures of molecules, and we should be able to show that polarity when we draw it as well. We'll learn how to calculate and use formal charges. Again, that might be new. Even if you've been able to do dot structures with a polarity, showing that polarity in your molecule, looking at formal charges might be completely new. Also, drawing resonance structures might be completely new. We'll learn to classify organic compounds and identify functional groups. So those are the things we're going to be hitting in this chapter. And we're going to start off with chemical bonds. Now again, bear with it. For the first session, you might remember a lot of this. It might be old hat. You might kind of know the answers already, but there might be some details in here, some different ways of looking at things before we get to some of the new stuff. All right, so chemical bonds. These are the attractive forces that hold atoms together in complex substances. And again, we could be molecules or ionic compounds. So of course the question comes, why study this stuff? Well, changes in these bonding forces are the underlying basis of chemical reactivity. So one way we can understand chemical reactions then is to look at how things are connected. And then of course, more importantly, we can start to predict how we can make things once we understand the trends of how these things react. So during a reaction then, what we're looking at is how we're going to break bonds and how we're going to form new bonds. Now, of course, there's two classes of bonds. And again, these will be some very familiar terms. We have covalent bonding. That means we're going to have a molecule. And if you remember, the key word for covalent was sharing. We're going to share the electrons. The second type of bonding we have is ionic bonding. And of course, these are what occur in an ionic solid. And here the key word is transfer. So for covalent, we're looking at the sharing of electrons. For ionic, it's the transfer of electrons. A lot of times we'll say ionic bonding is a little simpler to understand because we can see where the electrons are going from and where they're going to. And so we're going to start with ionic bonding. So ionic bonds then are the result from attractive forces between oppositely charged particles. Since we're going to transfer an electron or multiple electrons, then we're going to have opposite charges. And those opposite charges then will attract to each other. So for instance, sodium chloride, we know sodium gives away its electron to the chlorine. And so we get an Na with a plus, we get a Cl with a minus. And of course, now we have opposite charges, and so they are attracted to one another. We know the metal, the non-metal bond is going to be ionic because number one, metals are going to have low ionization energies. That's what we've been talking about with oxidation and reduction just a couple chapters ago. It's easily going to lose electrons in order to be stable. And of course, we know that the nonmetals then have very exothermic electron affinities. In other words, they want to accept those electrons. Okay? Now, another factor that's going to go into these things is what we call the formation of a lattice. The lattice is basically how these charges are interacting with each other. And they're going to form a lattice or a network that's going to actually typically give us energy. So that's also going to be energetically favorable. So ionic compounds then are formed from a metal and a nonmetal. We know that a sodium will transfer an electron to a chlorine. That means the sodium will then be attracted to the chloride and we will form sodium chloride as a solid. So the ionic bond itself is actually the attraction between those oppositely charged particles. So why does this occur? Why is the electron transferred? Why is sodium plus and not sodium 2 plus? Or why not sodium minus? And again, we can ask these same questions for chlorine. Right? You might want to refer back to some of our simple answers, but in this chapter, we're going to be looking at some more complex reasoning that goes along with it. So I mentioned not only do we have the charges, but we have this lattice energy. So remember, all these compounds, whether they're ionic or covalent, exist in a three-dimensional pattern of some sort or another. For salts, we call it an array. So exist in three-dimensional array of cations and anions. And again, that's going to be referred to as a lattice structure. So you're going to hear a lot of these terms are being interchanged, right? You can use it pretty interchangeable: lattice structure, three-dimensional structure, dimensional array, these types of things. Now, your ionic chemical formula is always written as an empirical formula, so we always know the smallest whole number ratio of cation to ion, right? And now to figure out this lattice structure, let's take a look at energetics and how we're going to figure this out. What we have to look at is the energy of the system in order to answer those questions. Why not 2 electrons? Why only 1 electron? Why not an opposite charge? For any stable compound to form from its elements, the potential energy of the system has to be lower. So in other words, right, there has to be a net decrease in delta H of formation. It has to be less than 0. Remember that negative that shows us heat is coming out of the system. What are factors contributing to energy lowering for ionic compounds? So in other words, how does sodium become sodium plus? How does chlorine become chloride? Now, what we can do, since we don't know the energies of things individually, is we can lean back on Hess's law again. We know that energy has to be conserved, and so we can envision a couple of different pathways here. So first, that lattice energy, we're going to take these random molecules, or particles, atoms, ions, and we're going to put them into a structure. So the amount of the potential energy of the system decreases when 1 mole of solid salt is formed from its gas phase ions. So what that's telling us is that to go from a gas to a solid, no matter what, no matter what, to go from a gas to a solid costs energy. Energy will be released when the ionic lattice forms. So we're going to cost energy to go from a gas to a solid, but in this case, those oppositely charged particles are going to have an attractive force. So when we form a lattice, right, the energy is going to be released. So there's a single step idea here where we can take a sodium, we can react it with half a chlorine, we get sodium chloride. We know the delta H of formation is measured to be negative 411.1 kilojoules per mole. Now the second way we can look at this and evaluate the energy is to look at the different steps that have to take place. For sodium solid to go to sodium gas, it's going to cost us 107.8 kilojoules per mole. For half a chlorine to become a chlorine, it's going to cost us 121.3 kilojoules per mole. That means, so far, we're running a positive balance. Sodium becoming a sodium plus an electron, in other words, the ionization energy for sodium, 495.4 kilojoules per mole. Chlorine to gain an electron, negative 348.8. So we can see that chlorine wants to gain the electron, right? So it's actually going to give us energy in order to accept that electron. Now bringing these two together to make a solid is negative 787 kilojoules per mole. When we sum all of this up, we're going to arrive at the same negative 411.1 kilojoule per mole. All right, so again, just applying Hess's law to our single step formation and looking at all the different steps that are involved. Now your lattice energy will always be exothermic, right? So you're always going to have a delta H lattice. It's going to be negative, which means it's always going to be exothermic. So they want to form this lattice. The lattice is a good thing. Delta H lattice gets more exothermic, in other words, a larger negative value, as ions of opposite charge are brought closer together. So just to form the ion, that might cost us energy. To get it into the gas, that might cost us energy. But when it gets two opposite charges and they start to come closer, remember the potential energy piece, right? That potential is going to go down because we're going to get the actual energy of that bond. Ions tightly packed with opposite charged ions next to each other. So we can actually calculate this out by looking at delta H lattice. It's going to be the Q positive times the Q minus divided by the distance, right? So any increase in PE due to ionizing atoms is more than met by decrease in PE from the formation of the crystal lattice. So again, any increase in potential energy due to ionizing them will be met by bringing those two opposite charges together, okay, even for +2 and -2 ions. Therefore, forming ionic solids is an overall exothermic process, and they are stable compounds. All right, so assuming that the separation between cations and anions in the lattice is nearly identical, which species would have the greatest lattice energy? Okay, so assuming that the separation between cations and anions in the lattice is nearly identical, which species would have the greatest lattice energy? Sodium chloride, 1-to-1, both +1 charges. Calcium chloride, the calcium is a +2, chlorides are both -1. Calcium nitride, right? So now you have a calcium with +2, nitrogen with a -3, and you'll have 2 calciums and 3 nitrogens. Sodium oxide, 2 sodiums, 1 oxygen, the -2. Calcium oxide, -2 +2. Now remember, all the distances are supposed to be the same. That's one of the assumptions we're making. Not a very good assumption, but it's an assumption, which means we're looking at solely charge, right? And which ones have the greatest charges? And of course, that's going to be C. And that's because you have the highest charges, a +2 and a -3. Okay. Which combination below will have the most negative lattice energy? So low charge ions, high charge ions, large distance, small distance. So we just saw that the higher the charge, right? So we go back to that last one, the higher the charge, right? The higher the lattice energy. And of course, by higher, we mean more negative because it's an energy we want exothermic, so we want a negative. So we probably want high charged ions, and then it's based on distance. Do we want them close or do we want them far away? And obviously, if we want to decrease potential energy, we want them to be small distances, right? So that's going to be D. So remember, it's the differences in your charges. So as Q increases, delta H will increase. And of course, as the distance increases, delta H decreases. So we want a smaller distance there. Okay, so why do metals form cations and nonmetals form anions? So we learned this by looking at the periodic table. Now we want to put some reasoning behind it. So the metal then is on the left-hand side of the periodic table. We know that the ionization energy is small and positive. In other words, a little energy is going to be required to remove those electrons. The EA is small and negative or positive, not favorable to attract an electron to it. In other words, it doesn't want an electron, which is why it doesn't cost us much to get rid of an electron. And then least expensive energy-wise to form a cation. So it's going to be a lot easier to take electrons out than to put electrons in. How about for the nonmetal? Obviously, we're on the right-hand side of the periodic table. We now see that our ionization energy is large and positive. Okay. In other words, it's difficult to remove an electron. They don't like to lose their electrons. The EA is large and negative, right? So it's electron affinity, EA. It wants to add the electron, and it's exothermic. It's going to be a large amount of energy given off when it gains an electron. So the potential energy of the system then will decrease. And of course, it's least expensive energy-wise to form an anion. And that's because it's hard to pull an electron out, easy to put an electron in. All right, so electron configurations. This is how we're going to figure out how many electrons are being moved back and forth. So you might need to review this. I'm going to go through this kind of fast. We just saw this not that long ago. You're going to follow the alphabet ordering. In other words, we're going to build up. So electron configuration based on filling an atom with electrons follows the order in the periodic table. We learned how to do it with our noble gases, electron configuration based on increasing value of N, and then at any given energy level by increasing values of L. So we saw the quantum numbers in the last chapter. Now we're going to look at electron configurations of ions. So how electronic structure affects types of ions formed. Okay, an example then. If I look at sodium, sodium's electron configuration, if you recall, is 1s2, 2s2, 2p6, 3s1. We can abbreviate that with a noble gas. We can say it's neon 3s1. If sodium were to lose one electron, take a guess at which electron it would lose. Well, it's going to be the opposite of the alphabet, right? We've built up the electrons. Now when we take them out, we're going to start at the top and work our way back down, which means we're going to get rid of the 3s1. That's going to leave me with neon. So electronically, its electron configuration resembles that of a noble gas. So the first ionization energy is 496 kilojoules per mole. It's very small and it's not too difficult to give you that. So it's very easy to get sodium to turn to sodium +1. Now, to get sodium to turn to +2, look at that increase there, 4,000. We went from 500 to 4,500, right? 9 times. So that's large. I'm even saying 10 times larger of an effect. So removing the first electron doesn't cost us too much. That can be done. Can't remove that second electron though, as I can't regain lost energy from lattice. So in other words, in order to get that electron out, it's hard to break the lattice apart. And so therefore Na2+ won't form. All right, we can do this again with calcium. So we know calcium is going to be argon 4s2. We know that calcium typically forms a +2 charge. So what 2 electrons are going to come off? That's right, the 4s2. That means we're going to form basically, electronically, it's going to look like argon. The first ionization energy, only 600 kilojoules per mole. Again, not too difficult. A little harder than the sodium was, but that's because we're pulling a second electron out. They have to add up, right? Second electron, there you go, not too difficult either. Trying to get the third one though, back up to 5K again. Too difficult, can't get it done. And again, you can regain the lattice energy around 2000 as long as you're making a +2 charge. Okay, and here we're doing 16, a little bit over 1600, 1700. But that third electron, way too hard to remove. Can't recoup any kind of required energy through a lattice formation. So forming a lattice is not going to give us the payoff, the dividend of the investment of pulling that third electron out. All right, we get good payoff for the second one, no payoff for the third one. Therefore, calcium 3+ doesn't exist, doesn't form. So, stability of noble gas core above or below the valence electrons effectively limits the number of electrons that metals lose. And of course, we learned this as the Octet Rule, right? This is the magic number 8. All of our noble gases are 8 electrons, and that's the name of the game. Ions formed have noble gas configuration. This will be true for both the anions and the cations. So if we look at chlorine, all right, chlorine we know is going to be 3s2, 3p5. What's it want to do? It wants to gain an electron. It's going to end up looking like argon and completing that p orbital. So adding another electron requires putting it into the next higher end shell. And that energy it's not going to cost too much, right? So that energy cost is going to be too high to go into the next level. So to fill the third level, not a problem, but trying to put one more electron into chlorine. So chlorine, it wants that first one. We go to put the second one in, and that's not going to like that because it's going to have to add a whole nother energy level. So 1s2, 2s2, 2p4. If we simply add an electron, we're going to get about 141 kilojoules of energy off of that. We go to add a second one, and it's going to cost us 844, right? That means it's going to be endothermic, but only to 700. So the energy required to form the cation is more than made up for, again, by that increase in the delta H lattice. So For oxygen here, we gain 1 electron, it likes that. We give it a second electron, it's going to cost us, but when it goes to form its lattice structure, it will get energy from that will more than compensate that 703. So when ions form then, atoms of most representative elements, S&P block, tend to gain or lose electrons to obtain the nearest noble gas configuration. And of course, that's the rule we kind of walked in knowing, right? Now, except helium, which only has 2 electrons, all noble gases have 8 electrons in the highest end shell. And again, that's the octet rule. So atoms tend to gain or lose electrons until they have achieved outer valence shell containing octet of 8 electrons. Okay. So octet rule works well for ions of these metals. Octet rule does not work well for ions of the blue metals, which is pretty much all the rest of them, right? So group 1A, group 2, that works. Aluminum, it works. Everybody else, not so much, okay? So again, 1A and 2A in aluminum. Nonmetals, it works well. Hydrogen and helium can't obey it, obviously. Only room for 2 electrons there because it's N equals 1 for that shell. It doesn't work with transition metals or what we consider to be the post-transition metals. Okay, so it doesn't work well for those at all. So what is the correct electron configuration for cesium and cesium plus? So here are your options, cesium and cesium plus. So if we go to our periodic table, we find cesium, we see it's in group 1A, right? Period 6, so it's going to be 6s1. We're going to go past xenon. If we take 1 electron away, it's going to be xenon, so that's going to be A. What charges are aluminum, phosphorus, sulfur, strontium, and rubidium most likely to have when they become ions? So give you a chance to pause here. And again, so aluminum we know is in group 3A. We expect that to be a +3, which means we can eliminate this one, and this one. Phosphorus we know is going to be on -3. So we can eliminate this one, and so our answer should be C. We just double check. Sulfur should be a -2, strontium should be +2, rubidium should be +1. All right, so what about transition metals? Because that was a lot of stuff there that will not be included by the octet rule. And so we're going to end this at segment 1 with 22 minutes in, and that's where we're going to pick up. So we're going to pick up with how to deal with electrons in the transition metals and see if we can't make sense out of some of those variations of charges. So stay tuned for that.